In this video, I'm going to talk you through how to work through the velocity problems that you did in a group yesterday. I know there was some confusion as to what all the variables were, so I'm going to step you through in this video each of these three velocity problems. These are from slide 10 in your electronic notebook and also from your group workspace. So this first problem, we have a rabbit that's traveling from 0 meters to 7 meters. And it takes the rabbit 0.46 seconds to cover that distance from 0 meters to 7 meters. What is the average velocity of the rabbit is the question. So if we zoom in here, so if we were to sort of draw a picture of this, here's our rabbit at 0 meters, okay? And then if 0.46 seconds later, the rabbit is over here at 7.0 meters. Okay, so in this drawing that I've made over on the right, to the left is our positive direction. Okay, so remember with velocity, we're going to report not only how fast the rabbit was moving, but also a direction using a positive or negative sign. Okay, so here in the problem, we are given an initial position. The rabbit travels from 0.0 meters. So 0 meters is the initial position. And the final position the rabbit gets to is 7.0 meters. And then we need to find the change in position, because in our velocity equation, if we're trying to find the average velocity of the rabbit, we're going to use this equation here. We're going to take the change in x, or the change in position, divided by the change in time. So in order to find that change in x, we take our x final, which happens to be 7. We've already written that down. 7.0 minus 0, and we're left with still 7.0 meters. Okay. And then we also are given some information on the time. We know it took 0.46 seconds. So if we're at 0.46 seconds over here at 7 meters, then at 0 meters, that was when like the stopwatch was started. So that would be the initial time would be 0 seconds. So here in our picture, over here on the right is our initial conditions, and over on the left are our final conditions. So we have 0 seconds as the initial time, and 0.460 seconds is our final time. So we take our final minus initial, so 0.46 minus 0 equals 0.460 seconds. Okay, so now we need to take our change in position, so 7.0 divided by our time, our change in time, 0.46. Okay, and when I take 7.0, so if we get out our calculator, we take 7.0 divided by 0.46, we get, well, a lot of decimal places, but in science, everything is a measured value, so looks like we have 2 to 3 sig figs. So you could answer, a correct answer for this class would be 15 meters per second, or 15.2 meters per second if you wanted to round to 1 decimal place. 15.2 meters per second. Okay, and we don't need to write anything in here for the velocity. That's actually what we were trying to find. So that was a question mark initially for our given values. Okay, so that's the first problem. The first problem, we were using this first equation here because we were trying to solve for velocity. Okay, let's take a look at the second problem. So we have a hare traveling at 4.5 meters per second, and it's negative 4.5 meters per second. So meters per second is our clue that we're looking at a velocity. Okay, so negative 4.50 meters per second is that velocity, and the hare travels for 600 seconds. Okay, and we want to know what the rabbit's change in position is. Okay, so we know the time, so they did it for 600 seconds. That means the initial time, and this is true most of the time, we're going to set our initial time equal to 0. And our final time is 600 seconds. So we have 600 minus 0 for 600 seconds. And if we are trying to find the change in the rabbit's position, well, that's this equation here. The second equation gives us the change in position equals velocity times the change in time. Well, here we know the velocity, negative 4.5 times the time, which is 600 seconds. I'm gonna run out of space in here. I should have made those longer for doing this on OneNote. So we have negative 4.5. So here, let's clear our calculator. And we have negative 4.5. Actually, I think I have to press the negative after. Times 600. And we get negative 2,700. Okay, now I got to think about what our units are. Well, if our negative 4.5 was in meters per second and we're multiplying by seconds, well, that leaves us with units of meters. Okay, so those were our units. We're left, our seconds cancel out, and we're left with units of meters for the answer. Okay, so that is our response, negative 2,700 meters. That's going to be our answer for number 2. And you could go back, and if you wanted to, you could put that up top here for delta x, but you really didn't have to. This was a question mark. We didn't know it initially, and we needed to do a little bit of math to solve for what that change in position was. Okay, the last problem here says when carrying a large acorn in its mouth, a jackrabbit travels at an average velocity of 7.75 meters per second. So again, we see this meters per second. We know that's our velocity. 7.75 meters per second is our velocity. And we're asked how long would it take a jackrabbit carrying an acorn in its mouth to travel 2 kilometers? Okay, well, so we know we're trying to find our time because it asks how long it takes. Okay, and we know that if the jackrabbit started at 0 meters, so let's just set, here's our rabbit. There's our rabbit. If we set this equal to 0 meters, the rabbit ends up at 2.0 kilometers, or if we use our conversion chart, that's going to be 2,000 meters. 2 kilometers equals 2,000 meters. So instead of putting our distance down or our change in position down as kilometers, because we have a velocity in meters per second, we want a change in position in meters as well. So I'm going to write my final position as 2,000 meters. And then I take 2,000 minus 0 gives me 2,000 meters. Okay, and I'm going to use this third equation here that tells me the change in time equals my change in position divided by the velocity. So my change in position, and again, I kind of ran out of room there. So 2,000 should be what's in parentheses, divided by 7.75. Okay, so we clear our calculator, 2,000 divided by 7.75, and we get 258.1 or 258. And if we check out our units, well, we know we're solving for time, so it probably should be seconds, but let's double check that. So we have meters, or the units of our 2,000, divided by, so we're dividing by 7.75 meters per second. Okay, so that leaves us with units of 1 over seconds. But if you divide by a fraction, that's like multiplying by a reciprocal. So basically, we're left with just units of seconds. Okay, so we got 258 seconds for that last problem. Okay, so a couple key things to note here. You got to figure out which equation works best for you. They all are the same equation, but I've just rearranged them for you. So if you're trying to solve for velocity, use the first one. If you're trying to solve for the change in position, you use the second one. If you're trying to solve for the amount of time, then you use the third one up there. The other thing is to pay attention to your units. Okay, you want your velocity to be in meters per second. Okay, or occasionally it could maybe be kilometers per hour. Okay, our change in position. Okay, which is, right, our change in position is delta x, velocity is v. Our change in position, I can't spell, change in position is going to be in units of meters. Okay, and our change in time is going to be in seconds. Okay, so those are the units that we should have, or our time could be in hours, or our meters could also potentially be in kilometers. But most of the time, we're going to have meters per second for velocity, meters for change in position, and our seconds are our change in time. Okay, over here, these are the variables. So v, delta x, and delta t. Those are kind of like the placeholders you put in an equation to tell you what math you need to do. So those are variables. Those are not our units. Our units are meters per second, meters, and seconds for velocity, change in position, and time. Okay, so hopefully that was helpful, and hopefully you can get this completed in both your group workspace and then pasted into slide 10 in your e-notebook.